Okay, so far, to show the distribution of electrons in the molecule, we normally draw the Lewis structure. So the Lewis structure is a must because with Lewis structure we're showing the distribution of molecules or the distribution of electrons in the molecule. To show now the arrangement of the groups around the central atom. And we want to make sure that these groups stay as far away as possible from each other. We need to show the molecular geometry. So the first step when you draw a structure, you draw its Lewis structure. The second step, you want to show the arrangement of the groups around the central atom. So you're going to draw its molecular geometry. You're going to use the Lewis structure that you drew, and you're going to use it in order to figure out the molecular geometry of the molecule. So again, the molecular geometry is to show the arrangement of the groups around the central atom, making sure that these groups are as far away as possible from each other for the structure to be as stable as possible. So with molecular geometry, we have to consider the bond angle between the atoms. And it does depends on how many groups there are around the central atom. For example, if you have two groups, then the molecular geometry is linear. You've seen this in 115. We've talked about this and also in Gen Chem 2 and 116. So this should be familiar. If you have three groups around the central atom, then the geometry is trigonal planar. The bond angle is 120. Four groups, then the geometry is tetrahedral, and the bond angle, this is the ideal bond angle between the hydrogen and the carbon and the two hydrogens, which is 109.5. So this is what I have here. So this is an example of an atom that undergoes basically a 180 bond angle. This is linear compound with beryllium. Be does have two valence electrons. So this is a valence electron here. It has a valence electron here. This is in two groups. Basically in group number 2. It should be connected to only two groups, not more than that. And when it does assume a linear geometry. Same thing for a triple bond, a carbon triple bond, carbon C2H2. Okay, this is the Lewis structure. So the first step is to draw the Lewis structure, and the second step is to figure out the arrangement or to show the arrangement of the groups around the central atom. Here I do have two central atoms. So I'm showing how the hydrogens are with respect to the central atom, so you should show the bond angle. This is linear. Normally linear geometry is a geometry which is assumed whenever you have two groups around the central atom. If you have three groups around the central atom, then in this case, the bond angle is going to be 120. This is going to be planar. So the geometry is going to be trigonal planar in there. It can be assumed either in case of BF4 or BF3 or in case of C2H4. Again, you draw the Lewis structure. Once you draw the Lewis structure, you arrange the groups in a way according to their bond angle, in a way that they are the farthest away from each other and the most stable structure. And for this type of geometry, the bond angle has to be 120 degrees, so each of these carbons is planar. This means that everything here lies in plane. If you have four groups around the central atom, then the preferred geometry is going to be a tetrahedral geometry. To represent a tetrahedral structure, normally we represent it as two bonds in plane. One is in front and the other one is behind. There are two different types of arrangements where you have four groups around the central atom. One of them has the farthest apart groups as in terms of bond angle, which is 109.5, and the other one has the bond angle around the groups or between the groups to be 90 degrees. This is called square planar arrangement. Now, because the groups are very close to each other, these hydrogens now are close to each other compared to the two hydrogens in a plane that are farther away from each other. This is going to be the preferred geometry. The idea is the farther away the groups are, the more stable is the structure. So the higher the possibility that the structure exists. Now, in order to represent a tetrahedral geometry, because you want to draw it on paper, to represent it, tetrahedral geometry is represented as two bonds in plane, one in front. In front, this is a wedge. So a wedge is a representation of a group that is pointed towards you, okay? This is pointed towards you, and then behind is a dashed line. So a dashed line is used for bonds to be pointed behind the plane. This is the ball and stick model. If you have your molecular models, you can easily build that up. You have carbon, and you have here 4 hydrogens. So carbon and 4 hydrogens, and you can easily see that one hydrogen is going to be pointing towards you. This hydrogen is going to be in front. This hydrogen here is going to be behind, and there are 2 hydrogens that are in plane. Now, if you take that ball and stick model and rotate it, so just turn it around, then you're going to end up having all of these arrangements, and all of these are the same. So these are exactly the same because there's a free rotation around this carbon. You can rotate it 360 degrees. So the bond that was once in front, it can be behind. But just make sure that every time you have 2 bonds in plane, one in front, one behind. 2 bonds in plane, one in front and one behind. This is how we represent a tetrahedral geometry, or a tetrahedral carbon. If you have a lone lone pairs basically affect the geometry of the structure. And we're going to call it now a shape rather than geometry. So the lone pairs, basically, because they are present, they are going to squish the bonds. Normally, if you have a structure like ammonia, this is the Lewis structure for ammonia. You want to draw its geometry. Now, the geometry for ammonia is tetrahedral. Why it's tetrahedral? Okay, I want to remind you of this table over here. See that table? Now, this table is on eCampus. So please use this table, and this table is to show you how to draw and how to figure out the geometry and the molecular shape of compounds. In order to do this, the first thing that you're going to do is you're going to calculate the steric number. What is the steric number? The steric number is the total number of atoms bonded to the central plus the lone pair. In case of ammonia, the total number of atoms bonded to the central, in this case here, is 1, 2, and 3. So 3 atoms bonded to the central, and then you have a lone pair. The lone pair is considered to be a group. So this is going to be 3 plus 1 for the steric number, so it's going to be 4. So now, in order to look for the geometry of ammonia, you have to look at 4 here. Okay, so you have to look at 4 for the steric number for ammonia, and then ammonia has basically 1 lone pair. So it does have 1 lone pair here. The geometry stays the same no matter what the lone pair is, but what changes is the shape, because the lone pair tends to squish the bonds. Tetrahedral normally has a bond angle of 109.5, but the more lone pairs are present, the more the bonds are squished, so the lower the bond angle will be. For ammonia, since you have a lone pair up there, see, this is the lone pair. The lone pair for ammonia is going to squish all of these bonds in a form that the molecular shape is going to be now pyramidal. It's going to be trigonal pyramidal. The geometry is going to stay tetrahedral, but the molecular shape is going to be trigonal pyramidal in this case. So it's going to be kind of like a pyramid. See, it's kind of like a pyramid in there. Now the bond angle, instead of being 109.5 for the regular tetrahedral, because you have lone pair, it's going to be less than 109.5. How much? You don't have to know how much, but just know that it is less than 109.5 because of the presence of the lone pair. The more lone pair you have, the lower the bond angle. So water is another example of a tetrahedral geometry. Why? Because the steric number is total number of atoms bonded to the central, it's 2, and the lone pair here is 2. So it's going to be 2 plus 2, so we're going to still be 4, but now the bond angle is 0. Oh, I'm sorry, the bond angle is 2 in this case, or the lone pair, sorry. The lone pair is 2. So 4 and 2, then this means that the molecular shape is going to be bent. So see how am I representing it as a bent here? See how am I representing this one as a trigonal planar, like a pyramidal like that? So for the trigonal pyramidal, you should show one bond in a plane, one bond pointing towards you, which is a wedge, and the other bond pointing behind. For the bent, you should show it as a bent like this, making an angle. This is the angle here, and the angle is going to be less than 109.5, way less than 109.5. Two lone pairs, they're going to squish more the two hydrogen bonds. So the bond angle in this case is going to be 105 compared to 107 for only one lone pair. With respect to the, this is called the VSEPR table. We've talked about this in 116, and you've discussed that in 115. So with respect to that VSEPR table in there, in organic, we only going to be interested with the static numbers of 2, 3, and 4. Static number of 5 and 6 we are not going to be interested with, because static numbers of 5 and 6, this belongs to inorganic molecules. So we will not be interested in that. But in this sheet over here, it does have all the bond angles that you will need for the assignments, for your assignments. So if you have a static number, so this here is the static number. If you have a static number of 2 and a lone pair of 0, so a static number of 2 and a lone pair of 0, then your geometry is going to be linear, then the bond angle is going to be 180 degrees. The bond angle is going to be 180 degrees. Here there are no lone pairs in static number 2 and lone pair 0, no lone pairs, so they're not going to affect the bond angle. It's going to stay 180 degrees. For static number of 3, then you can have either a lone pair of 0 or you can have a lone pair of 1. If you have a lone pair of 0, no lone pairs around the central atom. And again, when we talk about lone pairs, we mean the lone pairs around the central atom, just the central atom, not on the atoms on the edges though. So if you have a 0 lone pair in there, the bond angle is going to be 120. So it's going to be 120 between the boron and the two fluorines. Okay, so all of those is going to be 120 degrees. Now, the moment you have a lone pair in there, the moment you start having a lone pair, then in this case, basically the bonds are going to be squished. And if the bonds are going to be squished in this case, then the bond angle is going to be less than 120. So the bond angle is going to be less than 120. So again, if you have 3 and 1 lone pair, it's going to be the molecular shape is going to be bent. The bond angle is going to be less than 120. The more lone pairs you have, basically this is going to be the lower the bond angle, but it actually depends on how many groups you have around the central atom and if it is possible or not. Okay, like for example here, over here where you have is with oxygen. So what you have here with oxygen in there, you do have a static number of 3, because with oxygen it's surrounded by one group and then 2 lone pairs. So one group and 2 lone pairs, this is an exception. One group and 2 lone pairs, this is a static number of 3, and then you have 2 lone pairs on the oxygen. Since you have 2 oxygens in there, you don't have a chance to have a bond angle less than 120. There is no way, because it's only 2 elements in there. It's only 2 groups. So they have to be linear, they have to be 180 degrees in that case. So basically this is an exception. Probably this sheet over here does not cover the lone pair 2. So the lone pair 2 here should have basically a linear molecular shape. And then if you have a steric number of 4, steric number of 4 means you have 4 groups around the central atom, including lone pairs. So if you have a steric number of 4, let's say for example CH4. CH4 has 4 groups. So a steric number of 4, it has 0 lone pairs. Then its geometry is tetrahedral and its molecular shape is tetrahedral. So you should draw it as such. I am giving you examples in this sheet of how to draw each molecular shape, including the lone pairs. So please make sure that you practice this, okay? The steric numbers of 5 and 6, we are not interested in those. These are, I'm gonna leave them for inorganic in case you decide to take inorganic. Okay, so let's have an example here. Draw the geometry of the central atom in the following. Okay, the central atom. So every time they talk about the geometry, they talk about the geometry of just the central atom. So I don't care about the geometry of the outside atoms in here. I only talk about the geometry of the central atom. So we're looking at the carbon, we're looking at the oxygen, we're looking at the nitrogen, when we're looking at the carbon over here. You guys, one more thing that I want to say. When you want to determine the geometry, you have to have the Lewis structure. So the Lewis structure should be there. So the first step, you draw the Lewis structure, which is already drawn for you. Well, this one it's not, so we're going to go ahead and draw the Lewis structure for it. Now with the Lewis structure, you don't show bond angles. You don't show anything because the geometry is the one that determines the bond angle. So you have the Lewis structure for each one of them now. Here you go. Now let's go ahead and figure out the geometry. The first thing that you would need to do is go to the central atom and calculate the steric number for each of these central atoms. So the steric number here is the number of groups connected to the central. How many groups I have? Not bonds, groups. So around this carbon I have 3 groups. This is 1, this is 2, this is a 3. Okay? There are no lone pairs around the carbon. So I am looking at the table of 3 and a 0. So that's it. I am looking, I'm going to enlarge this a little bit. So I am looking at the table 3, a steric number of 3. This is the steric number column. And a lone pair of 0. So a steric number of 3 and a lone pair of 0, then the geometry, this is going to be the geometry in there. The arrangement in pairs is going to be the geometry. And then this column in here is the shape. Okay? So the geometry here is going to be triagonal planar. Since 0, then it's going to be a triagonal planar in there. This is going to be our triagonal planar. It has a geometry and the shape of a triagonal planar. You want to draw it. So this carbon over here is going to be triagonal planar. You have to draw it. And I know that the triagonal planar should have 120 degree bond angle. So you should draw it. This is a carbon double bond O. So you take the Lewis structure and then you draw it as a triagonal planar. So this is my triagonal planar, and this bond angle over here, each of these bond angles is going to be 120 degrees. And this carbon is going to be triagonal. So you point at it, and the geometry is a triagonal planar. Do the same thing over there. Oxygen has 1, 2, 3, 4 groups. So it does have 4 groups. How many lone pairs? It has 2 lone pairs. Do you see that? 4 groups and 2 lone pairs. So 4 groups and 2 lone pairs. It is a tetrahedral geometry still, but the shape is bent. They are asking me about the geometry. Be precise. They are asking me about the geometry. Nobody is asking me about the shape. So I need the geometry. It's tetrahedral in there. This is how I need to represent it. I need to represent it as a bent. And I know the angle in there is going to be less than 109.5 because of the presence of the 2 lone pairs. So I'm going to have 2 lone pairs here. And that is going to be a CH3. and that is going to be a CH3 over there. And that bond angle normally, because of the two lone pairs, is going to be less than 109.5. How much? You don't have to know how much. It's basically 105 degrees, but it's fine. You don't have to know how much. It's like water. It's like water in there. For the NH2, again, this is 1, 2, 3, 4. We're doing the same thing. Static number 4, lone pair is 2. So again, the geometry is tetrahedral around the central atom, and the molecular shape around the central atom is bent. So you draw it exactly the same. This is the bent over here with the two hydrogens forming an angle less than 109.5. And see my lone pairs, how I'm drawing my lone pairs. My lone pairs are outside. This is my angle over there, which is less than 109.5 degrees. For the C triple bond, and the moment you see triple bond, then basically the geometry has to be linear. It cannot be as an angle. There is no way, because with the triple bond you do have two groups around the carbon. No lone pairs, so 2 and 0. So it has to be linear. Bond angle has to be 180 degrees, I'm sorry. So it has to be 180 degrees. So to represent that, you represent it basically as drawn. A carbon, a triple bond nitrogen. This carbon over here, it's going to be linear geometry. And the bond angle, you always need to show the bond angle is 180 degrees. Okay? We're gonna do the same thing over here. Okay, so I'm just gonna put it there. Okay, we can easily see. Okay, so we can easily see. Okay. So here you go. Just let me take those so that you won't get confused. Okay. So let's continue. Determine the bond angle of the following. It's already, the Lewis structure is already there. You cannot determine the bond angle before you have the Lewis structure there and you figure out the geometry of the molecule. So the Lewis structure is the first step. So the first step, get the Lewis structure. The second step, get the geometry. And the third step, you figure out the bond angle. Okay? So over here, triple bond, it has to be linear. So this carbon and this carbon over here has a static number of 2. So your geometry is linear, shape is linear, the bond angle is 180 degrees for each one of them. When you have a double bond means a planar, okay? Double bond means a trigonal planar, because this carbon over here, I want to know what's the geometry of this carbon here. This carbon here has 3 groups around its central atom, 1, 2, and 3. So 3 groups with a 0 lone pair, then the geometry is a trigonal planar. No lone pairs. So the shape is also trigonal planar. If it is trigonal planar, then the bond angle between those is 120, and the bond angle in here between the double bond and the chlorine in this case is going to be another 120. So to represent this is kind of like deceiving. To represent this is how it should be. So when you want to draw it, this is going to be a carbon, double bond carbon. See those two hydrogens? Those two hydrogens basically are going to form a trigonal planar. So the bond angle here is going to be 120 degrees, okay, between those two carbons. And then I'm going to have a hydrogen here and the chlorine there. So the bond angle between the two carbons and the chlorine is not 180 degrees as it is written here. It's just deceiving. Here all they just drew the Lewis structure, but from the Lewis structure you have to determine the geometry and then the bond angle. So when I determined the geometry around this carbon, I knew that this carbon is trigonal planar and this carbon is again trigonal planar. So you have to draw them as trigonal planar. So you're going to end up having a structure like this and then determine the bond angle. So the bond angle here is going to be 120 degrees. Okay, and same thing over here is going to be 120 degrees. Again, you cannot determine the bond angle like this. You have your Lewis structure. You have to change this into molecular geometry or shape. So carbon is connected to 4 groups. So steric number is going to be 4. No lone pairs on the carbon, so it's going to be 0. 4, 0. It's a tetrahedral geometry and a tetrahedral shape. So I need to draw it like this. I need to draw a carbon as a central atom. One bond is going to be pointing towards you. You choose. Here I'm going to make the chlorine pointing towards me. I'm going to make the hydrogen here pointing behind. This is how we represent a tetrahedral structure. And then the other 2 bonds, I'm going to make them in plane. I have a hydrogen and I have a CH3 over here. Now, once you draw the tetrahedral geometry, now I know that the bond angle between the hydrogen and the CH3, see that bond angle here between the hydrogen and the CH3? That is 109.5 degrees. This is the bond angle between the hydrogen and the CH3. And the same thing for the bond angle between hydrogen and the chlorine. This is again 109.5. By the way, I am getting all of those values for the bond angle from here, okay? I'm getting those values because again, if it's 4 and if it is tetrahedral, then the bond angle is going to be 109.5. So I'm having a bond angle here again between the hydrogen and the chlorine. This hydrogen and the chlorine bond angle is going to be 109.5. Same thing, determine the geometry around the highlighted atom. So this carbon over here is connected to 2 groups. So you have 2 and 0. Then the geometry is going to be linear. So this column here is for the geometry. Again, this column is for the shape. The geometry is going to be linear. The bond angle is 180. Same thing for that nitrogen. It has 4 groups around it, 0 lone pair. The geometry is tetrahedral. So the geometry is going to be tetrahedral with 4 groups. And tetrahedral means that I need to have a bond angle of 109.5. Now, with respect to organic molecules, of how to draw organic molecules, there are 3 ways to represent organic molecules. The first way is structural. This is the way that we use it for Lewis structure. And for structural representation, you normally show all carbon-hydrogen bonds, all CC bonds. So this means that you're showing all carbon sigma bonds or carbon-hydrogen bonds. Everything you're showing. And this is how you represent Lewis structure in there. So if I have a chain of 4 carbons, this is how I represent it. I show all the bonds between the CC and all the bonds between the CH. This is called a structural representation. So this is called structural. It's not always convenient to show the structural. Structural is the Lewis structure, but it's not always convenient to show, because if you have molecules that are big with a lot of hydrogens in there, I mean, you're going to spend a lot of time drawing all of these hydrogens and all of these bonds. So the better way to represent it is using the condensed, and the best way is to use the skeletal. So the condensed is what? It's basically you omit carbon hydrogen and carbon carbon bonds, so you don't show any single bonds at all, no single bonds. So you take out the bonds between the carbon hydrogens, so this becomes CH3, you write it down. This becomes CH2, you write it down. This is a CH2 and this is a CH3. Notice every carbon should have 4 bonds, so this is going to make the carbons on the edges. These carbons are CH3s, the carbons in the middles, they have to be CH2s. Now, I can go further and condense it further since it's called condensed. Since I have 2 groups that are the same, I'm going to link them together in the brackets and then 2. This means that I have 2 CH2s and then a CH3. So I have a CH3, I have 2 CH2s and a CH3. This is the condensed form for this structural formula. Now for the skeletal. For the skeletal, it's easy. Just count the carbons and you never show any carbon, any hydrogen. You just show bonds. This is the skeletal form. How you draw it? Normally you count the number of carbons that you have. I have 1, 2, 3, and 4. I have 4 carbons, so you go by one carbon, so you just represent carbons as dots. I have 1 carbon, I have 2 carbon, I have 3 carbon, and I have 4 carbon, and then you connect the dots together. Do not connect them as a straight line, so don't do this. The reason why, because see, every single carbon of those is a tetrahedral geometry, showing 2 bonds in plane. Okay, here you go, just to make it easier for us to see. Okay, so showing this bond is in a plane. Always make sure that the bonds across the carbon chain that are always in plane. This is easier. So I'm having this in a plane and another hydrogen in a plane. One hydrogen is in front and the other hydrogen is behind. So this is a hydrogen, this is a hydrogen, this is a hydrogen over here. I'm just explaining why I'm drawing it as a zigzag instead of drawing it as a linear, because it is not linear. The bond angle here is 109.5. This is a tetrahedral geometry. I want the carbons to be as far away as possible from each other. I don't want them to be on a straight line. I want them to be as far away as possible of each other. So if these two are in plane, one hydrogen is going to be in front, the other hydrogen is going to be basically, let's make this hydrogen in front, and the other hydrogen is going to be at the back. The other hydrogen is going to be at the back. So in this case, you're going to have the second carbon. Notice that these two carbons have to be the farthest away from each other, and the farthest away from each other is to assume the 109.5 degree angle. Same thing over here. I have one hydrogen pointing in front, the other hydrogen pointing behind, and then 2 bonds in plane. And same thing in here, 1 bond in plane, 1 hydrogen in plane, and then 1 hydrogen in front. Notice I can draw the hydrogen in front and behind anywhere I want. It's okay, it's fine. It's still a tetrahedral geometry for each one. My point is, when you represent a skeletal structure, you want to make sure that the carbons are the farthest away from each other. So you don't draw them in a form of a straight line, you just draw them in a form of a zigzag where the bond angle is 109.5 and the carbons are the farthest away from each other as possible. Now there are different types of carbons, and these carbons we give them a name. If you have a CH3 carbon, this is called a methyl carbon. A CH2 carbon, this is called a methylene carbon. And the CH carbon is called a methine carbon. So please know those names in there. This is another example of a structural formula with condensed. Take away all the CC bonds, all the bonds, and the CH bonds. Then you're going to end up having a carbon in the center. See that carbon in the center there? So this carbon in the center is basically this. This is the carbon in the center, and this carbon is connected to 3 CH3s. Do you see them? 1, 2, and 3. So you put the 3 CH3s in the brackets and put the 3 in there. So these CH3s, they basically belong to the CH. It makes sense. Why? Because when I want to draw it, I know that carbon should make 4 bonds. So I start with my CH, this is my CH, and then I should have 3 bonds around the carbon. Each one of them has a CH3. So this is a CH3, this is a CH3, and this is a CH3. So now my carbon has 4 bonds. This can be changed into skeletal form by simply getting rid of the carbons and the hydrogens. We don't show any carbons and hydrogens, we just show bonds in there. So to draw the skeletal form, I know that I have 3 carbons, so you just draw 1, 2, 3 carbons and 1 carbon in the center. This is the 1 carbon in the center, and you connect everything together, and this is going to be the branched skeletal form. When you have a chain of carbons, that chain of carbons, if it is not the branch, then we're going to call it an N chain. Okay, so like for example here you have a 6 carbon chain. This is an N chain. N chain means it's a straight chain. I want to change the Lewis structure into a skeletal form. Again, I don't have any branches in here to worry about, so just count your number of carbons. This is going to be 1, 2, 3, 4, 5, and 6. This is how you put them and then connect the dots together. If you have a cyclic structure, we will talk about cyclic structures because carbons exist as chains. They can be connected together in a form of a chain, and they can be connected together in a form of a cycle. In this case, you can represent the cycle in a skeletal form, and it's easier. You can see it's easier than the Lewis structure. The Lewis structure, which is the structural formula, it's so much crowded with all of these hydrogens. With the skeletal, I know that this carbon, since it has 2 bonds, it should have 2 hydrogen bonds. These are the 2 hydrogen bonds. Here again, this carbon has 2 hydrogen bonds, 2 hydrogen bonds, 2 hydrogen bonds, and 2 hydrogen bonds. And again, this carbon over here has 2 hydrogen bonds there. To represent the skeletal structure, all what you need to do is count the carbons and simply draw them as dots and connect them. So I have 3 carbons and then I have 3 carbons at the bottom. And then connect these carbons together. Okay, here you go. So connect these carbons together and you're going to end up having your cycle. More examples. Now here, this is a chain that has a CH3 as a branch. Do you see it? That CH3 is coming off the longer chain. So my longer chain here is made up of 1, 2, 3, 4, and 5 carbons. So here you go, 1, 2, 3, 4, and 5. I am drawing right now the skeletal form. So this is going to be the 1, 2, 3, 4, 5. Just connect them together. And then normally what I would do, I would number them. I am numbering them here just for the sake of drawing the branch to see where the branch is on the chain. So, okay, let's see, draw it neatly like that. So let's go ahead and number them. You can start numbering anywhere you want, this side or that side. I just want to see where the CH3 is on the chain. It's on carbon number 3. If you start numbering from here, start numbering from the same side on the skeletal form. So on carbon number 3, I know I have a CH3. So I know that I have a branch coming off like this. See the edge in here? See that carbon? This is a carbon. This is not a hydrogen, this is a carbon. So it's a carbon, and I know that the carbon has 3 hydrogens. So this is a CH3. This is a carbon. It's a carbon and it has 3 hydrogens. So this is a CH3. This is another carbon. It is not a hydrogen. It's a carbon with 3 hydrogen. So I have here always at the end of the chain is always a CH3. In the middle there are CH2s, and if there's a branch, this is a CH. If there's a branch in there. So now this is the skeletal. If I want to represent it as a condensed formula, then I would do it in steps first, since this is new to you. The first thing that I would do, I would take out the CH bonds and the CC bonds. So taking out the CH bonds and the CC bonds, I would keep only the branch bond, and then you take that branch bond out, take it out. That CH3 belongs where? It is on the CH. So you put it between the brackets and it means it's on the CH. So this CH3 basically belongs to the CH. When you want to draw it, it's part of this, it's coming off the CH. Now for the double bond, normally the double bonds for the condensed, you always keep, you either keep them or you take them out. It's like an option, but we prefer to keep the double bond. We can represent it as a further condensed formula and take out the double bond. So it's going to be a CH3CH and the CH and the CH3. So if I'm looking at this formula, there is nothing wrong with it. You should just need to know that here this carbon doesn't have 3 bonds. No, it does have 4 bonds because there's a hidden double bond in there. And this is why I said it's more preferred to write the double bond in the condensed form. So this is the structural, and here this is the condensed. Now the reason why I could have shown the hydrogens for the CH3 and the hydrogens for the CH3, but I ran out of space over here. But this is still the structural form, and this is the condensed form. To draw the skeletal for this one, count your carbons. It's 4, 1, 2, 3, and 4. Connect them together and then number 1, 2, 3, 4. So between carbons 2 and 3, this is 1, 2, 3, 4. Between carbons 2 and 3, you do have a double bond, just to draw the double bond like that. If you have a heteroatom, normally with heteroatoms we show the lone pairs in the Lewis structure or the structural formula, but you don't have to show it in the condensed or the skeletal though. But this does not mean that the lone pairs are not there. They are there, but you don't have to show them. What I have here is a CH. On the CH I have two CH3s. So see how I drew it. Instead of doing a CH3 here and a CH3 there, I took both CH3s, I combined them in brackets, and this is a 2. This means that these two CH3s, they are branched on the or from the CH. And then next to the CH you have a CH2, and then you have an OH. Same thing, idea here. Lone pairs are represented in the skeletal or the Lewis structure. In the condensed and basically the skeletal, you don't show the lone pairs, but this doesn't mean that the lone pairs are not there. No, they are there. If I want to draw the skeletal for this one, then it's going to look like this. I do have two CH3s branching off a carbon, so this is a carbon-carbon branching off a carbon, and then I have a CH2 over here. This is a carbon, so this is my CH. This carbon is a CH2, this is my CH2, and then here I do have an OH. This is how I draw the skeletal form for it. For the more condensed form of this structural formula, I have two chlorines coming off the carbon of the CH. Now the chlorines, I don't have to put them in the brackets. The reason why, because chlorine is one atom. CH3 is two atoms in there, a carbon and a hydrogen. So this is why I had to include them in the brackets. But here, I don't have to put the brackets around the Cl. So you just leave it like that. You have a CH, CH2, read it as you go. CH2, this is a CH2 over here. I have another CH2, I'm gonna group them together as CH2 brackets. This is twice. And then I have an O, and then I have a C, and on the C I have three CH3s. So these are my three CH3s. If I want to write it in a skeletal form, this is my CH. I start with the carbons first, okay? I leave the chlorines. So I'm having my CH. Now the CH is connected to a CH2, so this is going to be a CH2, and this is going to be a CH2 over here. On the CH2 I have an oxygen. And then next to the oxygen I have a carbon that has or is connected to three CH3s. On this carbon I have two chlorines. So this is a chlorine 1. This is, you have to draw the chlorines, because other than that you would assume that these are carbons, and it's wrong. Okay? At the end always of the skeletal form, you always have CH3s. So this is a CH3, this is a CH3. These are not hydrogens. These are CH3s. This is a CH because it's a branch, and this is a CH2. Make sure always that every carbon should have 4 bonds. Bond 2, so you should fill the rest of the bonds with hydrogens. Here 3 bonds, so you should have a hydrogen over there. Normally in the skeletal we don't show the hydrogens. So this is going to be the skeletal form for this condensed structure. Now, condensed structures with carbonyls. This is our functional groups in there. Carbonyls normally, they exist in a form of a carbon double bond O, and the carbon double bond O can be expressed or connected to basically different groups. So if you have a carbon double bond O connected to a hydrogen, this is called an aldehyde functional group. It's called an aldehyde functional group. And the aldehyde functional group normally is expressed in a form of a CHO. So if I have a molecular formula of CHO, then in that case, I know that it doesn't mean that the hydrogen is basically connected to the oxygen. This is not right. The CHO is a representation of the aldehyde, and the aldehyde is a carbonyl connected to a hydrogen. So this is basically how you draw it. This is the condensed form of the aldehyde. This is the condensed form as CO. A CO is a carbon double bond O. So if you have a carbon double bond O, then this is the condensed form of a ketone. So ketone is another functional group there. And this is how you represent it. You represent it as a condensed form as a CO. So if you see a CO in your molecular formula, in the condensed state, then it is a carbon double bond O. Now, if you see CO2H, CO2H means, this is my CO2H, means it's a carboxylic acid functional group. So it is a carboxylic acid functional group. It's going to be a carboxylic acid functional group. This is the CO2OH. And if you have a CO2 in your molecular formula like that, this is called an ester functional group. I'm just showing you those different structures of carbonyls because all of these are condensed formulas. So if you have a condensed formula so that you would know when you want to draw it out, how are you going to express it? How are you going to draw it? So a CO2 is a carbon double bond O. A CO2H is a carbon double bond OOH. A CO is a carbonyl, a C double bond O. And the CHO is basically a carbonyl with a hydrogen. All of these examples, this is the only way you can write down the carbon, and the carbon has 4 bonds, which is octet. As I mentioned, with the skeletal form, you don't show the lone pairs, but this doesn't mean that the lone pairs are not there. Please pay attention. It's kind of like deceiving that I'm going to give you this structure, and once we start reactions, you have to know that oxygen should follow the octet rule. Right now, it has 1, 2, 3, 4, so it needs to have lone pairs. It needs to have 4 more electrons or 2 more lone pairs. So it is like that. And it really matters because normally reactions start from the lone pair. So it matters where the lone pairs are. So you have to figure out that. Same thing, if I have this in form of a skeletal form, it's kind of like deceiving because I know that oxygen, to have 3 bonds, here it's having 3 bonds, 2 with the hydrogen and 1 with the carbon, and a plus a charge, it has to have how many lone pairs? 1 lone pair. So this oxygen should have 1 lone pair in there. My point is, keep track of your formal charges and keep track of your lone pairs. Skeletal forms, we don't need to show lone pairs, but if you want to show lone pairs, go ahead and show lone pairs. I don't mind. More examples of how to convert skeletal into structural formulas. And here I am doing it in steps though, but once you get trained with that, you can go from the skeletal immediately to a structural formula. Just know that this carbon over here is a CH3 because it has 1 bond, so it needs 3 hydrogens, and it is a carbon, so it's a CH3. So see what I did over here. The first thing, I added the carbons. These are the steps. Since you are starting with this, so you add the carbon. So I have a carbon here, carbon, 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 so carbons all the way, and this is an NH2, I keep it. And then you go ahead and add the hydrogens. So this carbon has 1 bond, it needs 3 hydrogens. This carbon has 3 bonds, it needs 1 hydrogen. This carbon has 2 bonds, it needs 2 hydrogens. So every single carbon needs to have 4 bonds in there. If it's missing a bond, fill it with a hydrogen, and then you get the structural formula. Same thing for this structure here. So I have a carbon here, I have a carbon here, I have a carbon here, and I have a carbon here. Normally for the triple bond, we don't show the carbons, so we show something like this. So this is this, we show it like this. This is the skeletal form of the triple bond, but this is kind of deceiving because there's a carbon here, there's a carbon here around the triple bonds, and there's a carbon in there. So the structure is 4 carbons. You show the 4 carbons and then add the hydrogens. Same thing. You simply add the hydrogens in there. This is a CH3. This is a CH3, so I'm changing this into a skeletal form. This carbon needs a hydrogen, so you add a hydrogen. This is a CH2, this is a CH2 and a Cl. You do the same for the rest. Now, if you have a charge on the carbon, normally the charge takes the place of one hydrogen, whether it's a positive or a negative. Remember, if it is positive, then the carbon is losing. So if you have a plus charge on the carbon, then we're going to call this a carbocation. So if you have a positive charge on the carbon, we're going to call this a carbo, because it's a carbon, and it's a cation. It's a carbo. I missed the O. It's a carbocation. It's a carbocation in this case. Now for the carbon to have a positive charge, it needs to have how many bonds? 3 bonds in this case. Right now it has 2, so it needs to have a third one over there. Don't forget, and its charge is a +1. For a carbon to be negative, then it needs to have 3 bonds and a lone pair. It is a negative charge. So right now it has 2. You add a hydrogen and you should have a lone pair. So you should have a 1 lone pair. Please remember that the negative charge takes the place of 1 hydrogen. Originally, carbon should have 4 bonds. So if you have a negative charge, take 1 bond out, add a lone pair. If you have a positive charge, take a 1 bond out, don't add anything. No lone pairs, nothing. Okay? This is an example, convert each condensed formula to a Lewis structure. So what I have here is basically, I want to convert it into a Lewis structure. So it's another way of saying convert it into a structural formula. Structural formula. Structural formula, you have to show the all the hydrogens, all the carbons, all the CH bonds and the CC bonds. So you start here. I'm gonna do it in steps. The first step, I'm just gonna go ahead and expand this a little bit. So we're having a C, this is a hydrogen, and I'm starting from here. Always start from right to left. This is how you, from left to right, this is how you write in English. So I'm starting with this carbon here. This is a CH3, so it's a carbon. This is a CH3 here. On that CH, I have another CH3. So see those 2 CH3s, when you combine them, these are the CH3 twice. They are on the CH. Let me erase this. So they are on the CH. So this is basically my CH there. And then I have my CH is connected to an oxygen. Do you see that? It's connected to an oxygen. The oxygen is connected to a CH2, so this is going to be my CH2 over here. And the CH2 is connected to another CH2, so this is going to be my CH2 over there. And this last CH2 is connected to an OH, so this is going to be my O and the H over here. Since I'm drawing the Lewis structure, I have to show the lone pairs. I have, and it's a must. Now I can expand those further, these CH3s, and so show them as carbons with the 3 hydrogens, as I'm showing in this answer. Same thing, but see how now here I'm having a CO2. A CO2, remember what I said last time, a CO2 is the same as a carbon double bond O and then O. Okay, this is what a CO2 is. This is connected. This is going to be connected. It has to be connected because the carbon needs to make 4 bonds and the oxygen needs to make 2 bonds and 2 lone pairs in order to be a 0 charge. So let's start. I do have a CH3. So I'm going to write it as a structural formula. So this is going to be my CH3. My CH3 is connected to a CH2. This is a CH2. How many CH2s I have? Look, I have two of them. So add them together or connect them together. These are my two CH2s. And then the CH2 is connected to a carbon. This is going to be my carbon. On the carbon, I have two oxygens. So this is going to be my first oxygen. This is going to be my second oxygen. Okay, so this is my first, my second. This is how a CO2 is written. And then next to the oxygen here, not this, this. Because this one over here is already octet. That's it. But this one is not. I need a bond in here to make it 8 electrons. So this oxygen is connected to a carbon, and the carbon is connected to basically 3 CH3s. So I'm having a CH3 here. You just write it as a CH3. Another CH3 here on that carbon. And another CH3 on that carbon over here. In your assignments, you have a lot of practice on those. This is another example in there. Show the skeletal structure of the following. So again, for A, you look at the carbons, count the carbons in the chain. So I have a CH3 here. Okay, next to the CH3, see the CH2s? I'm just going to go ahead and draw them. I have 4 of them. 1, 2, 3, and 4. All of these are going to be my CH2s. Next to the CH2, I have a CH. This is going to be my CH. On the CH, I have basically, see, on the CH, what do I have? I have 2 CH3s. This is one CH3. This is another CH3. So I have a branch on the CH. This guy over here, this is my CH. This is my CH. On the CH, I have a branch coming off. This is the methine carbon. So, so I am having here 2 CH3s. I am having a carbon here and a carbon there. This is the skeletal form for A. For B, I am having a carbon. So I'm starting with this carbon. On this carbon, I have a branch of 3 carbons coming off. So this is 1, this is 2, this is a 3. Now this carbon is connected to a CH, so this is the carbon is connected to a CH. This is my CH. So if it's my CH, it should have a branch coming off here, and the branch is basically the OH, because the OH is on the CH. It is on the CH. How do I know? It's a brackets. And if the brackets is basically after a CH, this means that the group belongs to the CH. And then I have a CH2, so this is going to be my CH2, and this is going to be my CH3. For C, I start with the CH always. This is going to be my CH. Off the CH, I have 2 CH3s coming off. These are my 2 carbons. The reason why I'm doing it as a ball like this or a point, just for you to know that this is a CH3. It's a carbon. It's not a hydrogen, so it's not a CH. It's a CH3. CH3 over there, and then on the CH over here, so this is going to be my hydrogen there. There's a hydrogen, but I cannot write it. This is skeletal. So on this carbon, I do have a CHO. We mentioned last time that the CHO is basically a carbon. This is my carbon over here that is basically connected to a double bond O. Okay, so we said that a carbon is connected to double bond O, and this is my hydrogen over here. If you want to show the hydrogen, you can show it. So a CHO is the same thing as a carbon double bond O and then H. This is an aldehyde group that is connected to another chain. So this is called an aldehyde group. Oh, I'm sorry. Yeah, we're done from the C. Now the D, I have a CH. Notice I always start with the CH over there. On the CH, I do have a CH2OH coming off and another CH2OH. Okay, move on. Now on the CH, I have a CH2 here. I have a CH2 here. I have a CH2 here. I have 3 of them. And then I have a carbon. This is my carbon. I have two CH3s coming off my carbon. So this is 1 and this is 2. And then on this carbon over here, I have a CH2. I'm here. And then I have a CH3. You notice when you draw, you want to make sure that every carbon does not exceed more than 4 bonds. So this carbon here has 4 bonds, so I am good. If I want to read it, a CH3 connected to a CH2, I'm reading it from here. It's connected to a C with two CH3s on it. So the CH3s are on the carbon here. These two CH2s, they are connected to the CH. But since they are CH2s, they are not a branch. They are from the longer chain. They belong to the chain. If they are a CH3, you just bring them off the chain as a branch. See the difference? If they are CH2s, then they are part of the chain. This is part of the chain. You have 3 of them. Let me highlight. You have 3 of them. This is 1, this is 2, and this is a 3 over there. And then off the CH, this is going to be my CH. So this CH is this carbon over here. This is my CH. You're having the CH2OH, 2 groups of the CH2OH coming off the CH. With respect to the electronic configuration, the electronic configuration of atoms is it's basically a way to explain how electrons they orbit around the nucleus and how electrons they are arranged in an atom. So far we know that the nucleus is the place for the neutrons and the protons. So this is the nucleus of the atom, and around the nucleus of the atom there are basically electrons that are orbiting around the nucleus. So you have electrons in there, they are rotating or orbiting around the nucleus. Now the electrons that orbit around the nucleus, they don't orbit randomly. They actually have a certain path that they circulate. And electrons, they orbit around the nucleus in shells. We call them energy levels. So the shells are basically n equal to 1 shell, n equal to 2 shells, so forth. So I have this drawing over here with the nucleus and the electrons around the nucleus. I just extended it a little bit there. Electrons around the nucleus, they orbit in shells. And the shells are divided into subshells. Now, normally the shells, we're going to call them n equal to 1 shell. We're going to give them a number 1 through 7. You have 7 shells around the nucleus where electrons reside. And these shells, we're going to give them a letter name from K to Q. So K is n equal to 1, Q is n equal to 7. Electrons, they reside in these shells. And to have electrons in these shells, we're going to divide these shells into subshells. And the subshells are the actual subshells that you are used to, the S, the P, the D, and the F. This is how you draw your electronic configuration. And this is how electrons are present in an atom. So the S shell, basically, it does have one subshell. And it has a capacity of 2 electrons. Normally when you want to add 2 electrons in the shell or the subshell, you want to make sure that these 2 electrons, they are opposite in sign with respect to each other. So this is why we represent them as spins. One is going down, the other is going up, because if both are going up or both are going down, they're going to repel each other and they're not going to exist in the same subshell. So the s orbital in here has a maximum of 2 electrons. The p orbital has a maximum of 6 electrons, and it is divided into 3 subshells. The d orbital has a maximum of 10 electrons, 2 in each, and it is divided into 5 subshells. And the f orbital has a maximum of 7 subshells, and it has a capacity of 13 electrons. Now the way to draw the electronic configuration, it's a simple way. You need to know this trend. So you start with 1s, 2s, 2p, 3s. The n equal to 3, the m shell, has s, p, and d orbitals. The N shell has basically, which is N equal to 4, has S, P, D, and F. So N and O shells, they do have both S, P, D, and F. This is the only two shells that have all the orbitals, the SP, the D, and the F. And then you start decreasing one shell at a time. The P has only the SPD and the 7 has the SP. In order to draw the electronic configuration, you do like that. It's going to be 1s, 2s, 2p3s, 3p4s, 3d, 4p5s, 4d, 5p6s, 4f, 5d, 6p, 7s in this order. And then 5f, 6d, and 7p. You don't have to memorize, only know how to draw this, and then you can do the arrows and write the electronic configuration. Make sure to know that S has only capacity of 2 electrons, the P has 6, the D has 10, and the F has 14, and then you're good to go. To draw the electronic configuration, all what you need to do is look at the atomic number. Not the mass number, the atomic number. Normally the atomic number is less than the mass number. It's the number of the atom in the periodic table. Carbon has an atomic number of 6, mass number of 12. So you always look at the lower number. This is the atomic number, is where the atom in the periodic table. This is what the atomic number is. And then this is going to represent the electrons. So you're going to go ahead and draw the electronic configuration. So the electronic configuration here is going to be 1s2, so you're going to start with 1s, 2s, and 2p. We're going to run out of electrons in there. I know that carbon is in a group 4, so carbon should have 4 electrons in its outermost shell. Carbon should have, we said that carbon has 4 valence electrons. This is, I'm explaining here why carbon has 4 valence electrons. Because it's in a group 4, yes, and as you can see in the electronic configuration, its lowest, it's basically its outermost shell. It's this shell which is the farthest away from the nucleus, is N equal to 2. That shell has 4 electrons. So the definition of valence electrons are electrons present in the outermost shell. And in the outermost shell, it is 2 electrons. 2 plus 2 plus 2, this is 6. The K shell is completely filled, so this is N equal to 1. This is not the valence electron shell. The valence electron shell is N equal to 2, where it has 4 valence electrons. Let's see, another thing that I want to say regarding electronic configuration is if you want to draw the electronic configuration, so let's say if I want to draw the electronic configuration of F minus, okay? So if I want to draw the electronic configuration of F minus, I know F is has an atomic number of 9. Fluorine has an atomic number of 9. So we're looking at the atomic number in there. Negative means that I am adding an electron. So now when I want to draw an electronic configuration for that, it should be 10 electrons and it should not be 9 electrons. So start 1s2, 2s2, 2p. Instead of being p5 for 9 electrons, it's going to be p6 in this case. So I have here a total of 10 electrons, because see that negative added to the 9, so I have to take into consideration 10 electrons in this case. So fluorine with a negative charge, not just regular fluorine. Fluorine with, I know that regular fluorine, F9, has a configuration of 1s2, 2s2, and 2p5. Fluorine is in the group 7, so the valence electrons has to be 7, and they are 7 in here. This is for fluorine. But if you're doing F negative, this is my K shell there, my L shell over here. So the valence electrons for the F9 are going to be, this is completely filled. So completely filled in there, the valence electrons in that case for the F9, they are going to be 8. They're going to be 8 in this case, so just add them up, and they are 8 valence electrons. In some books, it's going to tell you, yeah, I mean, this is 8, so keep it as 8. It's fine. Now, with respect to the valence bond theory and and how bonds form, we have different types of bonds. We have sigma bonds and we have pi bonds, and we are interested in both in organic. So we want to see how sigma bonds are formed. We want to see how pi bonds are formed. In order to form a sigma bond, there are three ways to form a sigma bond: 1, 2, and 3. To form a sigma bond, I know that any bond that I want to form, I need an overlap of 2 electrons. So if you have 2 electrons, if these 2 electrons, they overlap with each other, of course, when I say an electron exists in an orbital. And the orbital can be either as an s orbital, the s orbital has a circular shape, or a p orbital, it has a dumbbell shape. One thing that I forgot to mention, when you look at the s orbital in there, s orbital is a circle in shape, okay? Now, the s orbital has 2 electrons, so this is the subshell of the s orbital, and the s orbital has a capacity of 2 electrons. And normally the s orbital is basically a circular in shape. With respect to the p orbital, the p orbital is made up of 3 subshells, and each subshell has a capacity. When I say they have a capacity, this doesn't mean that they should have that number of electrons, but they have a capacity of 2 electrons in there. You have the px, you have the py, and you have the pz. This is the p orbital. To represent a p orbital is represented as a dumb shell, basically a dumbbell shell. So it's going to be having 2 lobes in there. So the px normally is represented like this. This is the px, okay? Px normally lies along the x-axis. So let's go ahead and draw the x-axis. Let's draw the y-axis in here. This is the y-axis. Py is along the y-axis, so this is the py, so this is the py, this is the px, and let me erase the s over here. We'll make more room up for the s. And then I have the pz, okay, so this is going to be my py using a different color there. And then I have my pz. My pz basically is on the z-axis. This is going to be my z-axis, and that is going to be my pz. Okay, so this is how you draw the p orbitals, the px, the py, and the pz. Normally, to make sigma bonds, this is the s orbital over here. The s orbital is circular in shape, and it has a maximum capacity of 2 electrons. In order to make a sigma bond, either you have 2 s orbitals, they overlap with each other. Each s orbital has 1 electron, as in the case of hydrogen. So if I want to represent the structure of H2, and I want to show its bonding, the bonding structure of H2, how sigma bonds are formed, then you have to draw the electronic configuration of the hydrogen. So I know that hydrogen is 1s1 because hydrogen has 1 atomic number, and the other hydrogen is 1s1, right? So the s orbital for the hydrogen, so for the hydrogen here, the s orbital is going to be just one electron in the s orbital. It's going to be 1s1. So 1 electron in the s, 1 electron in the s. They can overlap with each other. If they overlap with each other, they make a sigma bond. So this is the first method of making a sigma bond, by the overlapping of 2 s orbitals. Another way is to overlap the px of the p orbital, so the px of the p orbital, with the s orbital of the hydrogen. The s orbital of the hydrogen has 1 electron, and the px has 1 electron. So the electrons combine together to form a sigma bond. Every bond is 2 electrons. So again, the s orbital for the hydrogen is 1 electron. The p orbital is 1 electron. How did I figure out the p orbital is 1 electron? I'll give you examples on that as we proceed. Okay. Another way to make sigma bond is to overlap two px orbitals. So as you can see, px orbitals there, they are responsible for the sigma bond. To overlap two px orbitals here, this is an example of a carbon single bond carbon. This carbon is going to have a p orbital, this carbon is going to have a p orbital, each p orbital, because this is an electron, this is an electron. So this carbon is going to have one electron in its p orbital, this carbon is going to have another electron in its p orbital. So these are going to overlap with each other and they're going to make a sigma bond. An example of a pxs is an overlap between the carbon and the hydrogen. So if you have a CH bond, the carbon has a p orbital. How did I know carbon has a p orbital? Carbon is 6, right? So it's going to be 1s2, 2s2, and 2p2. It ends in p orbital. The p orbital has how many electrons there? It has 2 electrons. So I'm going to use one of its electrons. So one of the electrons in the px. So this is going to be the px, this is the py, the pz. I'm going to leave the py and pz to form double bonds. And I'm going to use the px just for sigma bonds. So the px has one electron. So this is how I'm saying that the p has one electron and the s has one electron because the s is 1s1. So it has one electron and there these electrons combine to form sigma bonds. Same thing here, I'm going to use the same rationale. This carbon has a px of one electron. This carbon has another px as one electron. The electrons, they overlap with each other and make a sigma bond. So for hybridization, with hybridization, it's basically explaining how sigma bonds are formed. So how you form the sigma bonds through combination of orbitals. Hybridization is to combine two or more atomic orbitals with each other to make a hybrid orbital. So let's have an example. An example like every other example that we do, carbon. So carbon 6, okay? Carbon 6 has 1s2, 2s2, and 2p6. Now with carbon 6, the first K shell is completely filled, I don't care about. I care about the L shell. The L shell is not filled. This is the one that has the valence electrons. So with carbon 6, what I have is the 2s. This is my 2s. And then the 2 p's. See the p's over there? They have 2 electrons. I'm trying to explain. If I have a structure of CH4, why carbon is making 4 bonds? Because right now, the way that I'm seeing it, carbon is making 2 bonds. Okay? So why carbon here is making 4 bonds? The reason why carbon is making, and all of these 4 bonds, by the way, they have the same size and they have the same characteristics. So there should be something going on with respect to the orbitals there. What's going to happen here is, since I have an orbital that is empty in the p orbital, I'm going to try to make this structure more stable, or this orbital combination to be more stable. So an electron gets excited from the lowest energy state, from the ground state, to a higher energy state. Gets excited, so see this electron here? It simply gets excited up to a higher energy state. That process, we call it excitation. Excitation happens when energy is applied. And excitation normally happens in order to form a more stable state. So here now what I have an S and I have 3 p's and all my orbitals are filled. Half filled. Still it doesn't explain, because the way that I am seeing it, 2p, then my carbon over here is making basically 3 bonds because of the 2p. It's not making 4 bonds. So scientists came up with the idea that, you know what, these orbitals, they don't exist like this. These orbitals, they exist in combination. They are hybridized. So you take the s orbital and the three p orbitals, and you combine them together. So the s is no longer an s orbital and the p is no longer a p orbital. You form a new set of orbitals which we call sp3 hybrid orbitals. In each of these orbitals you have one electron, and all of these orbitals, they have the same size, the same strength, and the same characteristics. And this is how we can explain that carbon is making 4 bonds over there, because carbon has an sp3 hybridization. Now, how to figure the hybridization? You don't have to write the electronic configuration every single time to figure out the hybridization. To figure out the hybridization, all what you need to do is, all what you need to do is look at the central atom, because hybridization is for the central atom. Count the groups around the central atom, and then use that same number of orbitals for the groups. Let me give an example. Carbon has 4 groups around it, right? So 4 groups around it, this means that I need 4 orbitals. I need an s and I need 3 p's. I know that the s is only 1 orbital and the p is 3 orbitals, so I need them all. So the hybridization of this carbon is sp3. Let's have another example. NH3 with a lone pair. Okay, this is the Lewis structure. Don't do hybridization before you do Lewis structure. So this is the Lewis structure. What's the hybridization of this nitrogen? Again, look at the central atom, because hybridization is only for the central atom. Look at the central atom, see how many groups there are connected to the nitrogen, including the lone pair. Including the lone pair. So here I'm having 1, 2, 3, 4 groups. So I need 4 orbitals. So I need an s and 3 p's. Okay? Let's have another example. Let's see carbon dioxide. Okay, so let's see carbon dioxide, and there's CO2. Again, draw the Lewis structure of CO2. This is the Lewis structure of carbon dioxide with 2 electrons in here, 2 lone pairs on either of the oxygens. Okay, what's the hybridization of the central oxygen, of the central carbon in here? Look at the groups that are connected to the carbon. So the groups that are connected to the carbon are how many? 2. They are 2. So the hybridization is basically 2 orbitals. It's 1 s and 1 p. So the hybridization of this carbon is basically sp. This is the hybridization. You look at the groups, and the number of groups corresponds to the number of orbitals. Let's have another example. BF3. Draw the Lewis structure, because I want to figure out if there is any lone pair in there. So for the BF3, there will be no lone pair. Get the valence electrons, distribute. So every fluorine should have a total of 8 electrons. So you will have nothing left over for the boron. Boron anyways is an exception. It does not apply to the octet rule. So here in this case, I do have the BF3. Now let's figure out the hybridization of the boron. It has 3 groups around it, so I need an s, and how many p's? 2 p's. This is 1, 2, and 3. So 3 orbitals for 3 groups around it. So the hybridization of the boron is sp2. Now, with respect to how you draw the hybrid orbital, we said that the hybrid orbital is neither an s orbital nor a p orbital, because it's the combination of the s and the p. If you combine the s, you combine the p, you're going to hybridize, and you're going to end up getting the hybrid orbital. So to draw the hybrid orbital, you're going to draw it as a large lobe. That top lobe includes both the s and the p. So you're gonna basically draw it as a 1 large lobe and a 1 small lobe. See the difference between the regular p orbital and the sp3 orbital. So now, if you want to draw the structure of CH4, I know that CH4 is tetrahedral. This is going to be my CH4 over there. So having hydrogen in front, hydrogen behind, this is the tetrahedral. Now what's the hybridization of the CH4? 4 groups around the carbon, so I am having a hybridization of sp3. Always a hybridization of sp3 means it's a steric number of 4. Okay, let me go back. I just want to put this over here. A steric number of 2 means it's a hybridization of sp because it has two groups around it. So I'm going by 2, 0. So 2, 0, this is an sp hybridization, so the bond angle is 180. Aesthetic number of 3, lone pair 0, so every time I'm going to say 3, 0 over there, then that is going to be a hybridization of sp2. So the hybridization here is going to be sp2. Aesthetic number of 4, lone pair 0, then I need 4 orbitals. Then the hybridization is going to be sp3 in that case. Why I'm going with 4 orbitals? Because here I'm going with the groups that are linked to the central atom. So if you have 4 groups that are linked to the central atom, then you need 4 orbitals, sp3. 3 groups linked to the central atom, then you would need 3 orbitals, sp2. And 2 groups linked to the central atom, you would need 2 orbitals, so it's going to be an sp hybridization. Now, in order to draw those sp3 hybrid orbitals, because over here, all the bonds around the CH, these are sigma bonds, and they are made up, so I have here 4 sigma bonds, and they are made up of the overlap of the 1s orbital of the hydrogen with the sp3 hybrid orbital of the carbon. And this is how you draw the valence bond representation. This is the same as that, just to show you how to draw it. So this is the hybrid orbital. I know that carbon has 4 hybrid orbitals because it is sp3. So it does have 4 hybrid orbitals in this case because I am forming bonds between 4 hydrogens. So I am having 4 s orbitals in there for hybrid sp3 orbitals, and each of these sp3 orbitals have 1 electron. From where I got this 1 electron? It's from here. I got it basically from, let me figure out, okay, I got it from here. So this, every hybrid orbital has 1 electron in it. Okay, where are we here? So you have an sp3 hybrid orbital on the carbon that overlaps with the 1s orbital of the hydrogen. Each one has 1 electron. So when these two overlap with each other, I should have drawn it like this. I'm just going to take this electron out, this electron out, this electron out, and this electron out, and simply put it like this, so that to show that I am forming a bond. Okay, just to show that I am forming a bond. The sigma bond is the overlap between the sp3 hybrid orbital of the carbon and the 1s orbital of the hydrogen. So it's the overlap. This is how I draw it. This bond, the sigma bond, is the overlap between carbon sp3 and hydrogen 1s. This is the sigma bond. So each of these sigma bonds in there, I have 4 of them.